probably time for something a little bit different. The geochemist's view of where we might be going in terms of the industry going forward and the links between geochemistry, geology and geophysics. And it was really pleasing to see the messages that have been coming out from people already in this session. And I think one of the key things that's coming out already today is that we are converging on a common, I guess, mindset about how we need to move forward. And that's really pleasing to see. So real-time data and geologically meaningful bumps. So the exploration challenge is probably summarised in a diagram like this. Certainly in the Australian context, this is the challenge we face. We're trying to explore for quite small systems beneath very complex geology, potentially under blind environments. And the kind of questions we're asking ourselves while we're drilling these things is, where am I? Where do I go next? And what is the cover I'm drilling through? So what do I know about what I'm drilling through at the time? And I think Steve Hill, as the director of the Geo Survey of South Australia, he summarised it really nicely when he was talking about this. He said actually the problem is not really so much where you put hole number one. The problem is, do we know, or can we find out enough from hole number one at the time we're drilling it to de-risk ourselves enough to put hole number two in and hole number three in? And in doing so, we then provide ourselves the possibility of vectoring that we wouldn't do from a single drill hole. Yet, our industry continually finds ourselves in a situation in these kind of geological environments where we've just got a single drill hole to go from. And if you really think about a mineral system, so this is my cartoon of a mineral system. So this is a cartoon based on some work we did at the Ranger uranium mine a few years back now, up in Northern Territory. And one of the beautiful things about science is that you can take very complicated systems, turn them into cartoons, and then everyone believes it. But in essence, you've got a uranium system there forming at a sheared lithological boundary, and then a set of zones around that are partly structurally controlled, partly permeability controlled, of varying mineralogy. And that mineralogical differences there relate to the chemical differences as well. And what we're seeing there, in the most part, in that whole cartoon there, is the mineral system captured in terms of the outflow of a mineral system. So we're not looking at the inflow there. Although I think Scott Halley, if anyone was in Scott's talk, you would have seen some really nice pictures of inflows of mineral systems where he was showing huge parts of the Zambian copper belt that have been depleted of copper. So this is the outflow of a mineral system. Now what's really critical there is that the mineral system really is made up of a number of things, and I think this has been touched on. There is the lithology. There is lithology built in there. But the lithology is not represented in the mineral assemblages. The mineral assemblages there are actually related to a combination of metamorphism and metasomatism. And yet, commonly in our industry, we see logging codes that mix metasomatism, they mix metamorphism, and they mix lithology, and we don't get consistency. The lithological boundaries there can be imaged because they are kind of contrast boundaries, they are textual boundaries as well. But those metasomatic zones we see, they often have gradational boundaries between them. And yet we often don't think about that environment when we're doing our geophysical inversions. So that's what a mineral system really looks like in reality. And all the way through that system as well, one of the other really fundamental things there is that in any of those zones, and in that outflow zone at the top there, in the convulging, in none of those zones do we find uranium. Because the uranium's all being deposited down at depth. Yet we find a lot of other aspects that tell us we're in the outflow zone of a uranium deposit. So that's the challenge we're dealing with. And it all comes back to how do we do the drilling and how do we learn about the rocks we're drilling through? Because there's only so far we can go with continuing to tweak our geophysical models. At some point you do have to actually bang a drill hole in and learn something about the rocks you're drilling through. The real challenge we have in the technology of drilling is that the drilling is just a cyclical process. Right? We drill, and we're drilling to take a sample, and we're measuring something in that sample, we're interpreting that measurement, and then when we're using that to say where we're going to go next, or our targeting, or something where we're going to put hole number two. And the real issue in our industry, in terms of the technology at the moment, is that cycle takes way too long to move around. So in Greenfield's diamond drilling, for instance, that cycle might take anything between 3 months and 12 months to move around, that single cycle. And that's just too long. In the iron ore industry, I've been getting my head into this a bit just lately, and if you go into a blast hole drilling, for instance, up in the Pilbara, that cycle at the moment probably takes 72 hours to move around, and that's actually too long. They want to move around that cycle in 24 hours. So it doesn't matter where you go and what kind of drilling you're looking at, that cyclical cycle is at the moment taking too long to move around. So that's a technology challenge. And really at the end of the day, what do we need to know about the rocks? Well, there's only 4 things we need to know about the rocks. So it's not really that hard, right? We need to know the petrophysical makeup, we need to know the geochemical makeup, the mineralogical makeup, and something about the texture or the structure. And actually, if you can measure those 4 parameters in any bit of Earth's crust you're drilling through, you can pretty well use those parameters for anything you want to do, all the way from grassroots exploration through to the mining process, mine optimization, through to remediation. So again, the technology challenge is how do we actually start to measure those parameters in a much more efficient way than we do currently. And of course, the geochemists turned to the geophysicists and realised that the geophysicists were running around with fantastic tools and technologies to kind of measure information. And the airborne platform is a really nice example of the fact that you take a single aircraft and you bolt a multitude of sensors on it and allow that thing to fly over a property, and then you've got all this data to play with. And the geochemists get a bit jealous about this kind of stuff. And of course, the geophysicists are playing around with these things, and at the same time, other people are doing stuff more related to geochemistry and mineralogy. So here's an autonomous platform. It's a sampling platform that goes around and measures the geochemical, mineralogical makeup of a bit of crust. Admittedly, it's a bit of crust on Mars. So this is NASA's Curiosity rover, the Mars Science Laboratory. But all that is an autonomous platform. It's a technology platform with sampling, sample handling, and a bunch of sensors on it, generating near real-time data. Right? So we're doing it on Mars, yet we don't seem to be doing it on Earth. Now, admittedly, NASA had a $2.5 billion budget. So you kind of do stuff like that. But actually we can learn from this. And actually we need to leverage off the opportunity of this technology being out there and learn from the way that sensors have been placed into airborne platforms. And I guess where my head has been at is looking at those 2 scenarios. Why are we not doing anything with drill rigs? So drill rigs are running around at the moment pretty much looking like they were 125 years ago, more or less. We're drilling, and we're not drilling a hole to drill a hole, we're drilling a hole to take a sample and learn something about the geology we're drilling through. Yet we're not instrumenting those drill rigs, we're not putting sensors on those drill rigs. Why are we not doing that? So I think the big step in the next few years will be that we will see the drill rig turn into a technology platform. And I think that's happening, and it's happening a lot quicker than people may appreciate. Already, if you go again to the Pilbara, you will find every single diamond drill rig in the Pilbara these days is mandated to have onboard sensors. So we're already measuring real-time drilling performance data while we're drilling through iron ore systems. And I think that's just the first step, and so I'll touch a little bit on where this might be going. But for the geochemists and mineralogists and geologists, this will be the technology platform that delivers us the kind of information that the geophysicists have been used to dealing with all these years. So near real-time analysis while drilling is the name of the game, in essence. And this is touching on some work that has recently come out of the Deep Exploration Technology, CRC, here in Australia, and probably just give you a bit of a flavour for, again, where we're going in this world. And this was a project that I looked after called Lab at Rig. And this was about recognising that in diamond drilling, in the process of diamond drilling, there's all this drilling fluid coming out of the hole. And that fluid contains crushed up rock, effectively cut rock. And if you look at the diamond drill bit there, there's actually quite a large area of diamond drill bit area relative to core. And it turns out that the mass of solid in the fluid is about equivalent to the amounts of core that you collect as well. So for 125 years again, we've been chucking away actually half of our sample that we've been spending money to drill. So we've been looking at technologies that allow us to recover the sample and present that sample in a way to sensors, so so that we can have near real-time analysis while we're drilling. We've been doing some trial works of this technology. Here's a picture of the setup that Geoscience Australia, in collaboration with the TCRC, actually did some stratigraphic drilling in Victoria last winter. God only knows what people want to drill in winter, it's just beyond me, but anyway, it was absolutely freezing. And so we actually had a very friendly client out there, and we went out collaboratively to do this. And we were able to deploy some kind of early or manual concepts of the technology out there. So there's a diamond drill rig. In the middle of that blue box there is AMC's solid recovery unit. That box there, what it does is it actually recovers the solid material out of the drill fluid and returns clean fluid back down the hole. It basically allows us to get away with without needing sumps. It's very much an environmental purpose for that. But we've repurposed it in doing what we're doing. So here we go, here's some sampling of that gloopy mud coming out of the back of the SRU. So the drill fluid is turned into gloopy mud. The SRU does a lot of the heavy lifting in terms of getting rid of the fluid. That stuff's about 20% moisture. So this is again just some trial work, test work. So here we are sampling that stuff. And then so that's the miracle lies here. So there's some technology stuff that turns that gloopy mud into a dry, packed powder, ready to be presented to a set of sensors. So here we are, here's a couple of bits of Olympus sensor equipment. So there's a Delta XRF there on the left, and Olympus's XRD Terra system on the right. The Terra system actually is actually a commercialization outcome from some technology that's sitting on Curiosity. That's exactly the same technology as the Kenmin system that's sitting on Curiosity. So already we're seeing a vestige of that space exploration technology coming into our hands. So there's a couple of sensors. We've written some software to control the sensors. We place the sample, there's some barcodes to keep track of things. We place the sample in the sensors, we generate data. And what we do is we actually embed that into, we allow that data to be transmitted up through the ether, through 3G Wi-Fi, SAT-coms, into a product that we call Reflex Hub. Effectively, it's a cloud-based data management solutions type infrastructure. And that then allows us to sit somewhere else in the world and consume that data and do stuff with it. So for us, we can consume that data straight into something like IAGAS, which is a geochemical exploratory data package, and turn it into something else, or we can live time report that. So I was able to sit in Perth, for instance, and see the data coming out of the drill rig in Victoria within a few hours of them drilling through those intervals. Now, that's a big step change in where we've been up to date. And to give you an idea, the kind of data sets, there's one of the holes, Staveley O2, and that data through the middle there, this is XRF data, XRF chemistry, and here we've got quantitative mineralogy collected out of the XRD, and that data, like I say, is being delivered a few hours after they've drilled through the interval. And I think any geologist or geoscientist in the audience can see immediately the value of being presented to those kind of data sets in near real time while you're drilling. It allows you to start to make decisions about what's going on in that hole while the drill rig is still drilling that hole. And it's super, super valuable. I think one of the big questions that we are now asking our industry is, how will that workflow change your business? And that's an interesting question. But the issue is we're going to generate a heap of data. Okay, we're going to start generating a heap of data as we're drilling these holes. But the mantra in modern day society is, I want information, not data, and I want it my way. And a really good example of that is the way we look at, say, weather information. So here's the sort of way that the weather information is looked at in Australia. Okay, so you've got a bunch of distributed sensors and satellite data and all sorts of complicated stuff that's pulled together by the Bureau of Meteorology. And it's turned into a data set that is parked in a common format in a central place. And then we all run around with iPhone apps. And those iPhone apps are basically pulling that data out of that central location and presenting it to us in some way or another. Now, most of them present it as raw data, but actually you as a consumer have an absolute choice over which weather app you think is the best one and the kind of way you want that information presented to you. So you can have it presented in quite a complicated way, or you could have an app that, I don't know, has a pink rabbit on it with a sun on its head or something like this. Right? That's fine. The data's all coming from the same place, but actually we are making the choice about how we want to see that data. Another really good example, I couldn't have a talk without this picture, Ken, but another really good example of this, of course, is that when you look at the flight deck of an aircraft. And this is a really good example of what I'm talking about. So an aircraft, in essence, is some kind of pressurised aluminium tube with a bunch of sensors hanging off it, hopefully a couple of wings and a tail. But it's effectively got a few hundred sensors on it. I think on an A380 they've got something like, we did look this up the other day, 255,000 sensors on an Airbus A380. Now, if you were to present that raw sensor information to a pilot, you wouldn't get very far, okay? Because they wouldn't know what to do with that information, that data. So what we do is we process that data through a set of computers, various computers, and we present to the pilot information, and we present to the pilot the information that they need to make a decision about what to do with the aircraft at that particular moment in time. So we're taking raw data, processing it, and presenting it as information that's useful to support decision making. And where I think we're going to be going in our industry is exactly that workflow, but in terms of exploration, mine optimization, mine planning, and all of those kind of things. We're going to have sensors, we're going to have data, but we need to turn that into information. And so the new technology is going to need data analytics. It is going to need that to come to fruition, because we can't just survive on the data, the raw data alone. And this is just an example of the kind of workflow. A set of sensors here. We've got an analytics engine. Yes, someone can sit at a desktop with iGas and they can make their own decisions, but that's not scalable. When we know how we want to treat the data, to scale it, the only way we can scale those analytics is to park them off into distributed compute resources or cloud-based systems like this. And then the products will then end up in your final storage. It will have dynamic visualization and all that kind of stuff. Now, what's really interesting here for the researchers in the room is that I think one of the big research areas going forward is going to be the algorithms needed to turn this data into the right information. And that's going to be a really big research domain going forward. And I would like to see people tackling that aspect. As an example of the kind of things, once we start having raw data, so here's that Stavely 17 data again, some different chemical elements. But what I've done actually is I've plotted there an image, which is actually just the raw XRF spectra for each interval plotted as an image. And already when you just look at that raw sensor data, you can already see key domains starting to come out in that drill hole. So even without doing anything, you start seeing domains. But you can see that when geochemists now start to play with big data, which is where this is going, we can start to use fancy big data analytics to do stuff like auto-domaining our geology and our lithologies. We can, of course, use quite complicated analytics to do things as well. Here's an example. I put this in. This is probably the sales slide. So there's no such thing as a free lunch. Okay. But this is a new feature coming out in version 6 of iGas for those that use it in March, where we're looking at self-organising maps. And self-organising maps is a really neat way of actually taking quite large distributed data sets. Multi-element data is a really good example, and then bringing that together to look at the interrelationships so that we can quickly assess the kind of domains that sit in our data. So this is geochemists starting to get into this kind of environment. And that's not about taking the decisions away from the geologists. It's actually about supporting the geologists, so allowing them to see information as well as the data so that they can quickly assess what's going on in that information. Hopefully actually take some of the pain away from the geologist so they actually do have more time to behave as geologists. That's a really important aspect of this whole workflow as well. We can get into some really fancy stuff. This is some work that June Hill from the CSIRO has been doing through the DET CRC, where we're actually starting to look at multi-scale wave analysis of downhole data, for instance. And that's about sort of saying, actually, at different scales, what do my domains look like in my multi-element data down a drill hole? So you can start to make assessments on the texture of my data down a drill hole. So as long as the technology is producing the data, we can actually start to use these kind of analytics routines to provide lots of extra information about our drill hole. And we can do all of this using the infrastructure at the time we're drilling the drill hole. And that's really important. Now, there was some discussion about petrophysical properties. I think one of the outcomes of this work will be that we will see, and the link back to geophysics, will be that actually we can use this information, we can use this data, the chemical data, the mineralogical data, to start to calculate petrophysical properties or predict petrophysical properties in the rock. Now, it's not perfect, but it's a damn good start. So here's some work that Richard Chopping did back in the PMD days. So 2008, there's a beautiful report. That was a collation of all the mathematical approaches that turn mineralogy or chemistry into predictive petrophysical properties in rocks. And we can start to use some of that and play games. If we're generating quantitative mineralogy from XRD down every drill hole, we can then use that information to start making predictions on petrophysical properties. That picture in the middle there is calculated hardness in red, calculated density in black, down one of those Geoscience Australia drill holes. And we can do that absolutely at the time we're drilling the hole. So you imagine taking that first, again it's wrong, right? We've heard a lot about models are wrong, the numbers will be probably wrong, but they're a damn good start and they're a lot better than having nothing. And so we can then start to take that information and bring it back into the geophysical inversion models as constraints, for instance. This is some work again that I did with Richard, where I was taking reactive transport models. So predictions on mineralogical distributions around mineral systems. Here we see distribution of calcite and chlorite above a porphyry system in a reactive transport model. So this is pretty serious, nerdy geochemical stuff. But at the end of the day, you get a prediction of geophysical, of mineralogical distributions. So you can then turn that into a prediction here of density, for instance, and start to play these forward modelling games that Ken alluded to, start to play forward modelling games about what does it mean when I see that in my mineral system. And there what we're seeing, of course, is a change in the gravity response that is not related to anything to do with the lithological geometry, but merely related to the presence of carbonate in an alteration chimney sitting above that gold deposit. So alteration of metasomas is a metamorphism. Just as a bit of a thought experiment, I don't know how I'm going for time, but there was a fair buffer built in by various things. So just as a thought experiment, I just thought I'd take people on a bit of a workflow, an example workflow of maybe where we're going to be going in not too distant future. So here's a 3D plot of some drill holes from an iron deposit up in the Pilbara. Showing iron there coloured up on the drill strings. That data set has about 9,171 data samples there in the drill strings along a channel system there. And so I took that data and I said, well, okay, we'll take the XRF chemistry there that we potentially should be producing in real time, and we'll turn that into a density using just a simple kind of algorithm there related to the mineralogy. And so how are we going to do that? Well, the first thing we need to do is we need to turn that chemistry into mineralogy, because it's the mineralogy that is going to affect your density, not the chemistry. And there's a number of different ways of doing that. If you don't have quantitative XRD, there's actually a number of different methods for trying to estimate chemistry, estimate mineralogy from that chemistry, as long as you've got a good validated chemical analysis. So there's a bunch of different ways. We can take normalization approaches. We can do some matrix inversions. There's some optimization methods that we've been working on, some least squares and linear programming approaches. We've got an algorithm working at the moment that gives us a pretty good assessment. So we can basically take that full multi-element analysis and we can make a pretty good prediction on the mineralogy that sits in the rock, particularly if in something like an iron ore system where you kind of have a rough idea of roughly what should be there. So we can turn the chemistry into mineralogy, and then we can apply that equation and turn the mineralogy based on the known density of the mineral phases into a rock density. So here's that mineralogy, the calculated mineralogy versus the calculated density. I'm just plotting a set of bivariant plots there. The quality is not very good on the screen, but basically density on the bottom axis versus a set of those minerals. And in the middle here we can see the quantity of magnetite, for instance, and this is coloured up by quality of the ore, which is a function of magnetite over magnetite plus goethite in this case. So this is high-grade ore here, or high-quality ore here, and we can see that trend there is obviously going up to the magnetite would have a density of 5.1 or so, which is that data point there. So that trend there takes us up to the magnetite density. So we can see a bunch of domains, I guess, within that data set when we look at that data set like that. The quartz is really nice, how we can see different domains in the quartz plot there, and we can start to pull out those domains. And then, of course, that's all very well looking at it like that, but at the end of the day, we need to know what it looks like in 3 dimensions. We need to know the spatial relationships, not just the data relationships. So here are those same set of drill holes with different angle, just to confuse people. Same set of drill holes now, coloured up by density, and we've calculated that density through a couple of steps there using analytics. And again, there's no reason why we couldn't be doing that with the infrastructure we have right now, right today. We could be doing that in real time as we're drilling those drill holes. Of course, we can then model that density. So here I'm just using a radial basis function in Leapfrog to model that density, that calculated density. Use the block modelling feature in Leapfrog to turn that into something that is starting to look like a constraint that you might use in a geophysical inversion. So what I don't have here, of course, is the gravity response or the magnetic response or something over the top of this. But where I think we need to be going is then using these approaches, these workflows, will drive us to make the connections between the world of geology and geochemistry and geophysics, because we're going to be providing these near real-time constraints into the system. And you can see also that what I'm doing there is parameterizing that information on 25 by 25 metre blocks. We could be parameterizing the chemistry there. We could be parameterizing things like crushability, rock hardness, all of those things we can calculate from that data. We can bring the geophysical data, if we've collected it at high enough resolution across that system, bring the geophysical data in to help us interpolate from our drill holes out to the broader area. And there you've got all of the constraints you need to do a really decent mine plan. Why are we not doing it? Just an example again, come back to self-organising maps. I talked about domaining. I think domaining is really important, particularly in the mining operations. We want to know the domains in our system. From an exploration point of view, we want to know the domains related to the mineral system. In a mining operation, we want to know the domains related to the value, I guess, and Steve and Alan touched on this very early on this morning. We could have domains of value. Self-organising maps, again, is a way of starting to domain out there. These are heat maps. I just love this data. This is a heat map of that data I've just shown you. The heat maps basically show you if the heat spots occur in the same place, they have basically a self-similarity. What you can start to see there is you can actually start to break out key assemblages in that data, key mineral assemblages, and we can start to cluster that out then, and then populate those domains, the spatial domains, back into our Leapfrog model. So that's all done off the basis of first pass calculations from the chemistry. So let's go and collect the chemistry routinely with the technology and then start to do this kind of stuff. So we're going to be doing this in real time. So what I showed you there was an after the fact exercise, and we often see after the fact exercises. But the reality is that technology is going to allow us to do that same workflow as we're drilling. So as our first fence of drill holes goes in, we'll make a first stab at it. As the next lot come in, we'll refine and reassess our model, and so on and so forth. We'll make decisions as we go, because there's no reason why we shouldn't be doing that right now. And so we're going to be working in a world where our 3D models, our geophysical inversion models, are going to be dynamic. We're going to reassess them continuously as we are drilling, as we are progressing our project forwards. The service companies are working very hard at the moment to make sure the infrastructure is in place to do this. This is a vision that the service industry has absolutely got in their heads, and are absolutely driving. Interoperability between products, interoperability between service companies, and the infrastructure to make it happen. So this isn't kind of a far future vision I'm presenting. This is something that actually is just around the corner. An example of the kind of things that we're doing, so I kind of showed a bit of this picture, is then turning that information into geometrological properties. And I said already that these kind of analytics are going to be required to be deployed into kind of computational environments on the cloud. That's just the nature of it, because they're going to be big data problems. They're going to need a lot of computational resources, but that's fine, because we'll learn from other industries. I think Steve showed the genome stuff. We'll learn from the way that people have done this before, and we'll take that on board in doing our stuff going forward. So again, probably another no freeload slide a little bit, but the reality is the drill rig is going to be, if it isn't already, a technology platform. We're going to be measuring drill rig performance data. We're going to be doing analysis while drilling. We've got downhole information. All of that stuff is going to be collated, integrated, pushed through communication methods to a central location. So it doesn't matter where the drill rig is, doesn't matter where the geologist is, you'll be able to see what's going on. We're going to present information to the end user in the way they want to see it. And in that workflow there, that end user could be a drilling contractor. They want to know about how their fleet of drill rigs is performing. But that same data might be turned into physical rock properties and given to the geologist in that way. So single data source, two different bits of information. So that's what we're going to do. Online analytics is going to be really important, and it's probably the cutting edge of research going forward. And seamless interoperability between these systems as well is going to be really important. In the way they've got it in the oil industry, we're going to have to see the same interoperability in the minerals sector. So the industry challenges are forcing us to reconsider the way we do business of mineral exploration and mining. There's no two ways about it. Timely decisions are critical, so we need information to support our decision making. That's the name of the game. It's not data, it's information. We need to integrate our geological and geophysical information to provide meaning to the bumps that we see, both in the geochemical bumps and in the geophysical bumps. We're also going to have to deal with customizable data management, storage and analytics. People want information in the way they want it. Okay, and that's just the name of the game these days. And drill rigs are becoming, probably drill rigs are today, technology platforms. You need to have a think about what that means for your business. Actually, the drilling contractors are fast worrying about what that means for their business. Are we going to start charging, are we going to continue to charge by the meter of drilling, or are we going to charge by the quality of data coming off the technology platform? And what does all of this mean for research, development, algorithms, and the skills of our people? And I think one of the really critical take-home messages here in terms of our people and the new generation of people in our industry is that we're going to have to see a lot more multi-crew resource training, where we actually park geologists and geochemists and geophysicists together in the same room working off these common data sets. We're going to have to see that interoperability between our business units a lot more than we have today, because this is going to drive us there. So I think I'll leave it there. Thank you very much.
Any questions? Yeah. The sort of flow from chemistry to mineralogy and then the jump to density is, well, from mineralogy to density is relatively straightforward.
Yep.
Okay. As somebody who's fairly obsessed with magnetics, I'm just wondering how good is your calculation of, say, magnetite or pyrrhotite contents in silicate rocks or in carbonates, given, for instance, the old CIPW norm, right, always overestimates magnetite because it doesn't include hydrous minerals like micas and amphiboles and things that partition a lot of the gobble up a lot of the ferric iron. Yeah. So how good? How good can you do?
Yeah, look, the algorithms required to turn chemistry into mineralogy, they've been played around with for a while. We're working on some stuff at the moment. It does a reasonable job. It's certainly a good first pass. I think my sense is that, of course, at the same time as we're doing that, we're working on rapid quantitative XRD technology that actually will give us the right answer. There's some algorithms required there to turn a wiggly line into mineralogy. I think in the first instance, if I was to say right now, today, what are the errors? I don't know, they're probably 5%, 10%. But you know, I think it's the cutting edge of where the research needs to be, is actually pinning down those kind of algorithms. And we haven't been doing it. And that's a great field for people to get their heads into because of exactly that, those aspects. So I think it will just continue to improve.
Yeah, just a couple of comments, and big one for stealing ideas from oil and gas. And I think one of the things you left off your list of what you need to be doing in a borehole is looking at structure.
Yeah.
So there's a big thing.
Yep.
And the second thing is that what you just said before about going from chemistry to petrophysics, in fact, what most of the people in this room need to be doing is going from petrophysics to geology, which is the inverse problem, which is much harder.
Yep.
But much more important.
Yeah, and yeah, I agree with both of those comments fully. And I think, Ken, you were talking about the Ford modelling thing. You know, Richard and I did some stuff back in 2008 where we played a game between Ford modelling a predicted alteration system. I haven't seen a lot of people do that since. Let's get out there and start doing it.
I liked your the airplane dashboard. Not well, my younger son's a commercial pilot, but anyways, the issue of complex, inherently complex, even if the displays are simple, but conflicting results. There's been a couple of examples recently where pilots behave poorly, turning off the working engine, for instance. Air France guys not climbing properly because their pitot tube was jammed. And I worry that we're going to be having a lot of data that we're going to be overwhelmed with that. I mean, you look at the, you know, you have the geophysical platform, and it's great, but we leave so much data on the table and never really interpret it because we're either unsure of what to do with it, we don't have the algorithms, or we don't have the people. And I don't think that geochemistry is going to have any hall pass on that. You're going to be, there was the lady from Hobart talked about engaging more algorithms, but you have to have somebody write these things that have some idea what it's all about. And then we have to synthesize that and try and look for changes. Will still be subtle changes in that. And you know, SOM is great, but it's the typical SOM thing. You've got yourself about 20 different little, you know, glyphs to look at, and it's like, whoa, you know, that's not simplifying it necessarily. It's a way we have to go, but I think there's a lot of time has to be spent on data synthesis that we haven't really done. Fine, we're not sending drones out to blow people up in Yemen. It's not life-threatening like an aircraft, but it's all this investment in technology. If we're really not pulling out what we think is important, we're going to be missing the boat.
So I think one of the that's a good point. So you know, and I can't agree more with the fact that training our people into this new world is going to be critical, and we need to understand what the new world looks like and make sure people have the right training. One of the things that is going to happen around things like the way that we're dealing with consuming data from the tools into the data storage systems, one of the things that's happening in that new world is we're automating the process of things like your QA, QC, and your data validation and those kind of things. And that process actually takes up more time from our geologists or geochemists now than anything else. If you ask a geochemist in the industry how much time do they spend doing QA, QC reports versus anything else, it's a significant amount of time. Now I think the infrastructure and technology will automate that process because it is eminently automatable, right? There's no reason why it shouldn't be, which I think will allow people time, even though we're providing new data sets, information, I think people will have more time to actually think. And I think that's really important. Hopefully.
Given the variability with geology in some types of deposits, do you think the maps like you showed before with the drill holes that you inferred that the geophysical properties could be subject to a bit of accuracy, like problems terms of accuracy? Have you compared it to like a map of geophysical map of properties, with the actual drill,
So I haven't gone through the exercise of finding a convenient data set where we have both geophysical maps and the data available to do this exercise. That exercise was done about 2 days ago. So yeah, I'm open to that actually, and I think we should be doing more of it. The variability in all bodies. I mean, at the end of the day, if you're in a mining environment, of course, at some level, you're going to abstract your variability to a scale that makes sense in terms of mining anyway. So at some point, it has to move from the academic realm to something that's practical. Things like the wavelet sort of modelling of downhole data is really interesting, because what it does is it actually is a way of domaining the drill hole by the texture in the data. So actually, you might actually be in a situation where you're domaining your ore body not for the key properties, but actually for you might domain it on the basis of variability, for instance. So that's really important, that kind of stuff. But yeah, I think we're just at the cutting edge of some of this thinking.
Yeah, it was an excellent talk, thank you. One comment is that why not just measure the magnetic susceptibility at the BBC, so you don't remove that ambiguity. And my other question is, what about contamination? Once you've taken that drilling mud out, and now you drill your next rod, that fluid is now washing past all the sample above it. Are you not introducing, say, a nickel anomaly deeper down the hole than there is one, for example?
Yes, we've done a fair bit of, sort of into the details of that, but we've done a fair bit of work on that. We're lucky enough in the DET CRC to have a drilling test facility in the hills just outside Adelaide. It's a very, very horrible place to go and spend a week, all those wineries. But what we do have is we have access to 3 drill rigs there. We were actually able to do experiments. So we've been doing very fine scale experiments looking at exactly those features of drilling down at 360, 400 metres depth. It turns out that the lifting efficiency of cuttings out of the hole is incredibly good. And it has to be. So it turns out when you talk to drilling engineers, they're like, well, of course we have to lift everything out in time sequence. That's just what we have to do to mean you're drilling. And actually, if you're not lifting the cuttings out, the drill rig's the drill rig's breaking anyway. So we've done the experiments. We've looked at it. Everything stacks in our favour. The drilling fluids themselves, they actually almost solidify when you turn the pump off, and then they fluidise again when you turn the pump on again. Flow rates, velocities are very high, 2 metres per second. And the drilling powders are very, very fine as well. So all of those things we've looked at, we thought we'd have a lot of depth smearing. It turns out we don't, particularly if you're trying to deliver things at 1 metre composite, which is what we're trying to do with that technology. But yeah.
Anybody else? I probably know as many ex-murderers as I do geochemists, so I have to take advantage of that.
Maybe they're both.
But there's 2 things I've always wondered on geochemistry, and one is, and you're very much aware of it, the powerful modeling, forward and inversion modeling we have access to. Is there a day in your mind, and pick Steve's 2030 or whatever, when we can actually have numerical modeling capability in geochemistry to say, I have a porphyry system, it's gone through this weathering tectonic history, this is what the geochemical, and it's got this sort of cover, this age, this is what I predict this is going to look like. Other than just a cartoon that is just by the seat of the pants sort of thing. Do you think you're getting enough information coming in with these new platforms and the analysis you're doing that you can got the inputs into real 4D type geochemical modeling as we do with geophysics?
It's really tough. I mean, I probably spent 7 years of my career believing I was going to do it, and the energy level was drained to almost zero trying to do it. The reality, at some level, potentially, if we were only worrying about major mineral phases, We're not going to worry about trace elements. That's hard. If we're worried about major mineral phases, then potentially we could. Certainly, within the community at the moment, there is no focused effort to make that happen. Not really. And if you look at actually the people that were around in the 90s generating the kind of thermodynamic data we needed, they are very far and few now. So we don't have that focused effort either. So it has, I guess, that effort shifted. Do I think we're going to get there? Well, look, I mean, probably all I can say is I'm not aware of a focused enough effort in the research community that is even there now. So,
Well, the other one is a little bit easier, you can tell me to buzz off, but there's a combination I see of, like Scott's talk yesterday about doing really brilliant stuff. I mean, you had to have Scott in the equation, I think, to make it brilliant, because he said it only took a couple of days to review it all that. Whoa, $1 million worth of data, a couple of days? Boy, that went fast. But what would be is the focus of going deeper? What point do you think surface measurements versus getting things teased out of a tube drilling is going to be required? At what point do you say, hey, if it's half a kilometer down, forget it, or you're just going to back yourself in the corner and say, well, it's all about the surface material, it's all about the water flows, and that's fair enough. I mean, I know there's more complexity in geochemistry.
That's a really good question, and I don't have a picture of it, but someone did show a picture of the eastern goldfields of West Australia, and they showed. Steve, you might have this picture, but they showed the areas that are covered by drill holes and discoveries, and then all these blank areas. And you look at the blank areas and you think, well, why are they blank? Well, okay, they're undercover. And it turns out that the majority of them are under 20 metres of sheet wash gravel. 20 metres of sheet wash gravel in that environment is enough to render there to be no geochemical signal at the surface whatsoever. 20 metres of sheet wash gravel, that's where we're at. So there is plenty of environments like that where you're not going to get it from the surface, you just have to punch a drill hole. And there'll be lots of times when let's just put a drill hole in and get the information and figure out where we are.
Right.
Well, and hole 2 and hole 3 probably.
And very much the message from Scott is that if we actually think about this and drill small stratigraphic holes in the shallow cover space and look at the larger geochemical footprint, that's actually the search space that's most likely to deliver in the next 15 to 20 years, rather than the vision that I showed a little earlier. So we still have a search space to go through, which is geochemically blind at the moment.
Well, one of the other things I find, and I kind of commented to Scott about this in hopefully not a nasty way yesterday, but I know of some anecdotal stories, like Dave Lowell spent a large amount of money doing an AMI survey in northern Chile and apparently got Zippo. There's other people that are very keen on these, I think it's a CO2 or some sort of gas measuring technique, and then other people are so disparaging about it. I'm thinking, boy, that's really interesting. It seems like some of those might work under significant cover, but there's not enough clear demonstration test cases or whatever.
So I think the issue with those techniques, and I'm probably going about my limb here potentially, but if you take biogeochemistry, is a really good one where we've seen successes and we've seen failures, and still, despite the fact that biogeochem has been around for 20 years, we still have no sound scientific basis to understand the process that gives us a signal in a leaf, or a signal in a bark, or a signal in a spinifex bush. So we still don't know what the process is, and whether an area we're walking over is okay for biogeochem or not, or whether we sample the eucalypt leaves, or the spinifex, or the sheep. And so again, I think it's just an area where the research, the fundamental process thinking hasn't come to bear on the techniques. So the techniques have got ahead of themselves with respect to the fundamental process. So when does a gas bring a signal to the surface, as opposed to when doesn't it? And what is the real process? And that's a pretty hard science to do, but we're not seeing that being done.
There is another step in there, which is the whole purpose of today, which is instead of hoping that biochemistry or hydro generates the bunks, then we just look for the larger footprint. I think the data analytics side that Reflex is going down is going to answer a lot of the downstream processes, but we still got to start somewhere. And the starting somewhere is drilling holes. No matter what we do, it's going to be drilling holes. I'm not so convinced the first hole is as easy to drill as maybe you portray. But that's the part that we're going to get right. And Scott's vision is broaden the scope, the spacing, look back and don't look for the bump. Don't bother looking for the bump at all. Just get those holes in, spend the money on the upfront drilling, and then once we're in the system, everything else will take care of itself.
Steve, one question about that. You know, one thing was, so we're targeting bumps, and you have a mag anomaly, and you've got a pretty good idea if you've hit it or not. Like we've got a, you know, we're used to drilling bumps. You know, we hit the bump, or we, you know, we've got our success or failure. I'm just trying to wonder what, you know, we start looking at these bigger systems and putting strat holes in. When do you know, what do you know, it's going to be looking for more subtle signals. It may be more difficult to tell, particularly early on, are you in a system or not? You know, just this difference between when we test the bump. At least we sort of know what, you know, is success or failure on that bump. But it may be more difficult to tell when we're looking for these larger systems. We're looking potentially subtle signals and.
Exactly, that's the $64 million question. The question is, what can we do to work out size of deposits based on characteristics of systems? So, you know, the immediate characteristic would be size in the first place. The staging chamber that sits under Norilsk is bigger than the staging chamber that sits under Voices. The alteration system at Escondida is larger than the alteration system at Koliwasi. The sedimentary alteration system that sits around the copper belt is bigger than it is around Nifty. These are empirical observations. The question is, what else can we do to make that a little bit less arm-waving and a little bit more meaningful in terms of science?
Yeah, I'd also like to make the point that at that sort of level there's no such concept of failure. We have to get over that, is that a null result in the exploration can be a success, because it can still point you towards where you should go next, regardless of what the number is, regardless of what the feature is. It can still give you, it's still giving you information that you didn't have before. And I think that has to be built into these sort of analytics. It's not about only going out after the true positives. You've got to be able to deal with the true negatives as well. And we're not very good as human beings dealing with that, because we get attracted to the jam, just like the honeybees and the wasps. You know, we've got to learn to take value out of null results and work out what that means.
That's going to require, say, education, then not only just say the geophysicists, but say exploration managers as well, who are saying this is not actually a failure. Take something away from it. You know, I mean, it is a valid point. I suppose it's just trying to change that mindset too. And
yeah, well, I think I mean, what part of James's talk is about changing the business. We're going to have to change the way we think as well as the way what we do.
You know, it's a very good point.
The actual structure of the way that we put our thought processes together to engage with the data and the information that we're generating will fundamentally have to change. And if we build on the past, we will fail. We actually have to make a step change. But we have to throw away all the old thinking and say, well, given what we think we can do, well, the technology can deliver for us and to us. What should we be doing now? Forget what we used to do in the 1990s, what worked in the 1970s at Olympic Dam. Forget all that. What can we do now? And build on that.
What does this sort of technology do to our workflow? So what does the coil drilling do to punching through, instead of being cheaper to drill through 20 metres, what does it do to drill more 20-metre holes and drill for the system as a starting point rather than drilling for the bump? Because I can do it cheaper. So the whole workflow changes the way, this changes the workflow. This drives the workflow change.
One of the things that I see, James, that well, I guess, shoulder to cry on, but there seems to be a lot more fundamental questions still in geochemistry about processes than there is in geophysics. In geophysics, if we have something that comes out of the blue, it's probably a 95% chance it's a scam, and the community, seriously. Because the physics is pretty straightforward, it's been understood. As somebody said, I think this conference, Maxwell kind of encapsulated it all. There hasn't really been much change. And so we really look at variations on the theme, reduction of cost, high resolution data. But I listen to somebody like James and some of my other axe murderer geochemist friends, and they're still pondering things that could be really important from the point of view of, I would even call it low-hanging fruit. But there's not enough people really looking at these issues. And I'm not sure it's always just a question of money. I think there's often people with curiosity can actually badger away at these things if they're trained right in the universities and given the opportunities to work with good data sets. You know, I think to me, this whole going to the future thing, it's not we're not like the Germans building a giant Panzer tank that's going to crush the opposition and just one solution will fit all. If you can have a whole bunch of guys with motorcycles with much smaller weapons, you can probably cause a lot of disruption. And geochemistry, to me, really seems to be an area that there's just some darn good questions that haven't been answered.
Yeah.
They could be important. Maybe not all in Australia, maybe not the Ilgar, maybe the Gawler, you know, maybe in Queensland or overseas. It just, it's irksome. And I think, you know, we hear about the numbers of people, and I cited it in my talk yesterday about the limited number of geophysicists. But I remember at Exploration 07, somebody done a tally, because we had a geochemical component of that, and they said there's 26 practicing geochemists in the world, outside of Russia and China, and maybe India. And then I think in the next 5 years, 3 of them died. Right? And there was one of the majors, I think Vale was hijacking somebody from BHP, or BHP, so it was deck chairs on the Titanic. They were just moving these people around. There was really no new blood coming into the business, which to me is, you're almost below the threshold level of a real technology being able to move ahead. I mean, even with your ADS, I mean, you can only do so much, right? So. Anyways, John was supposed to lead us in 15 minutes of questions. John, you failed.